Alrighty, today we are looking at a topic we visited in the fall a little bit, and that is linear, quadratic, and exponential models. So today we're going to be looking at when we're looking at the line of best fit. So it's not going to be perfect, it's just going to be the best we can do to connect the data points we're given. And then we're going to use a calculator to do some regression. So you will need a calculator handy if you don't already. But quick overview. For a linear graph, we've got a straight line and we have a relative constant rate of change, aka our slope. Quadratics are parabolas, so we either go from decreasing to increasing or vice versa, and our second differences are the same. And then lastly, exponential, we've got that horizontal asymptote. We're either growing or decaying, and the successive y values will have a common ratio, is another way that we can identify when we've got exponential. So firstly, we are just going to recognize with a scatter plot if I've got a linear, quadratic, or exponential set of points. So I'm just going to graph each of these, and these are not exact. So I'm going to be doing a little bit of estimation with some of these. So, again, this would not be a perfect graph, but there is a clear linear relationship here, and my line of best fit would be a straight one. On B, I'm going to do the same thing. So I clearly go from increasing to decreasing here, so my line of best fit is going to be a parabola, which makes this a quadratic model. On C, I'm decreasing, but the rate of my decrease is not constant. So this would be an exponential model. And then last but not least, and this one again is going to be an exponential. So once you know that you've got a linear, quadratic, or exponential model, we can use our calculator to create an equation or a function, and we can use that regression to make predictions for future values. So we are going to do that for each kind, linear, quadratic, and exponential. Firstly, linear. So we are looking at the weight of newborn babies, where X is their age in months after birth, and W of X is their weight in kilograms. So what I'm going to do is put these values in a list. So in my calculator, this stat button is the first thing I'm going to press, and then enter for edit. And in list 1, I'm going to put my 5 X values, then arrow over, and in list 2, I'm going to put my 5 Y values. After that, I'm going to hit stat again, arrow over to calc, and that fourth option, linear regression, is what I'm looking for. I'm going to hit enter 5 times, and it gives me my linear function. So the weight, W of X, is 0.8x plus 3.34. So if that is my linear model, if I want to predict the weight of the baby 2.5 months after birth, well, that would be W of 2.5, and I'm going to plug in 2.5 for X, and I get that the predicted weight of that baby would be 5.34 kilograms. So similar steps are used when we're looking for quadratic and exponential regressions as well. You first start by putting those points into your list. So here I'm looking at the time after launching of a rocket and its height in feet, and the time is measured in seconds. So I'm going to go to Stat, Edit, and I'm going to put in my new X and Y values. And then going again to Stat, Calc, this time I'm going to do a quadratic regression number 5. And again, enter 5 times, and it gives me my quadratic, ax squared plus bx plus c, and it tells me what a, b, and c are. So the function for the height of my rocket, we'll just go to 2 decimal places for each of these values, negative 14.32 x squared plus 121.87x plus 0.36 is the function. And if I want to use that to predict the height of the rocket after 7.7 seconds, I am going to substitute 7.7 in place of x in that function. And doing all those calculations gives me an approximate height of 89.73 feet for the rocket at that time. So moving on to our final type of regression, exponential, we are going to go back to that list and put in our final set of x and y values. And then again, we'll Stat, Calc, we are going to scroll all the way down to 0 for an exponential regression. And there is my function. Again, we'll just go to 2 decimal places, and here is the value of a car. I should have said that earlier, but I trust that you can read the words that are on your paper. So that car is depreciating in value, and if I wanted to find the value of that car 12 years after it was purchased, well, I'm just going to plug in 12 for x into our model. And since we're talking about value, this is dollars and cents, I'm going to round to 2 decimal places. $1,727.08 is what that will get me. Okay, the final thing we're going to look at is how do I determine with just a set of data, is it linear, exponential, or quadratic, and then writing my regression. So those first examples we did, we were told straight away whether it was linear, quadratic, etc. Here, I need to first figure that out. So going on example A, I'm going to put my x and y values in here, and I have one too many, so I'm just going to hover over that and hit delete. And then I can add these in. Okay, so I've got my x and y's, and what I want to do is make a scatter plot. I want my graph to have each of these individual points so I can look visually and see what's going on. So I'm going to do y equals and turn on plot 1. And in stat plot, I see that plot 1 has list 1 and list 2, which is great because that's going to have my x and y values. And then I want to make sure that I adjust the window appropriately. So my smallest x value is 0, and I want to be able to see a little bit before that, so I'm going to go to -1. My biggest x value is 5, and I want to be able to see a little beyond that, so I'm going to go from -1 to 6. For my y's, my lowest is 904, so I'm going to do 900 just so I can see a little bit before. My biggest is 1023, so I'm going to do 1050 just to make sure I can see a little bit beyond that. And then when I hit graph, it shows me my points, and if I were to draw a line of best fit, to me, that would be exponential. So this is an exponential model, and so to get my function, I'm just going to go to Stat, Calculate an exponential regression, because my points are already in those 2 lists. So I can get my function. Again, I'm just going to round everything to 2 decimals, and there is my exponential function. Moving on to B, we're going to do the same thing. Okay, my plot's already on. I'm just going to go ahead and adjust my window to make sure I'm going to be able to see everything My smallest x value is 52, so I'm going to set it to 50 just to make sure I can see everything. My biggest x value is 89, so I'm going to make it 90. My smallest y value, it looks like, is 59, so I'm just going to do 55. And my biggest x value, or excuse me, y value looks like 89. So when I graph, this one is kind of all over the place. It's definitely not a parabola, and it's not quite exponential either. So it's going to have to be linear. And again, these models won't be perfect. They're just the best approximation we can make. So I'm going to calculate a linear regression with the data that's already in my table. And I think I did something wrong because those are not the right values. Let me go back to my list. That should be 84. There we go. So now let me calculate that regression. There we go. 1.02x minus 6.31. Okay, last two, wash, rinse, repeat. I'm going to put these values in my lists. And then I can delete the extras. And I'm going to adjust my window to make sure I can see everything I need to see. And I can clearly see from these points we go up and then down like a parabola. So this is going to be a quadratic. And I'm going to use a quadratic regression to get my function. Okay, and then last but not least on D, adjusting my window. And so we are increasing by approximately the same amount the whole time. So we're going to call this one, we're going to call it exponential because, again, we are not increasing by the same amount every time. The slope would not be constant. So we've got an exponential model, and I will just quickly do one last exponential regression there to get our function. And that wraps up our regression notes today.